Hello, in this video, I'm going to review some of the problems on the practice test for test number 2, which, as you know, is Wednesday, April 6th. So we're not going to review all of the problems on the practice test in this video. I'll do some in this video, and then I'll also do some in class on Monday, April 4th, prior to the test. And we still won't review every problem off the practice test, either on this video or in class, because some of the problems are pretty straightforward, and we've reviewed them frequently, either in the class notes or in your homework. Now, this test does cover a lot of material, so of course it's important to study well for the test, because this test includes trigonometry, right? Which was not included on test number 1. So that means the amount of material for test number 2 is more than it was for test number 1. Let's start with a very basic trig problem. This is really sort of the reason the subject of trigonometry was invented, is so that we could solve right triangles. So remember, solving right triangles means you're given a right triangle and you're given some information about the right triangle. Some information about the lengths of the sides of the right triangle, and some information about angles in the right triangle. And then you're asked to find the lengths of the other sides or the sizes of the other angles that aren't given in the triangle. So in this right triangle, notice this is a right triangle, right, because it has a right angle in it. We're given the size of this angle, and then also the length of this side, okay? And then we're asked to find the length of the side opposite the 60-degree angle that we're given, right? The length of the side x. But actually, we could find, eventually here, we could find the lengths of all the sides in the triangle, right? And then also the size of this other angle in the triangle as well. So we could look when we say solving a right triangle, it really means we're going to find, we can find the lengths of all the sides in the triangle and the sizes of all the angles in the triangle. But in this problem, we're only asked for the length of this side x, right? And of course, this is where our trigonometric ratios, right, come to our assistance, because we, as I mentioned previously, right, the side opposite the 60-degree angle is this side x that we're looking for. And the side that we're given the length for, 18, that happens to be the hypotenuse, right, of this right triangle, because it's 18 is opposite the 90-degree angle in the triangle, right? So the side opposite the 90-degree angle is always going to be the hypotenuse of the right triangle. So that means we can set up a trigonometric ratio, right, involving this 60-degree angle, and also involving this unknown side x, correct? Because the sine of 60 degrees, right, would be computed as the length of x, right, over the length of the hypotenuse, right? Sine is opposite over hypotenuse. Of course, you're going to have to remember the definitions of all your trigonometric ratios for this test, right? Those are covered in some of the prior problems on the practice test. So we know the sine of 60 degrees is the side opposite over the hypotenuse. So in this triangle, right, that's x over 18. And so what we end up here with is an equation involving this unknown x, and we can solve for x. Sine of 60 degrees is not an unknown to us, right, okay, because this value we can compute either using our calculator, right? So the calculator, of course, will easily compute for you the sine of 60 degrees. But since 60 degrees is a special angle, we should also have memorized that its sine is the square root of 3 over 2. So you don't have to rely on your calculator here for this problem. You can just write sine of 60 degrees is square root of 3 over 2, right? That's equal to x over 18. And then just solve this, this equation. In this equation, since you have fractions on both sides of the equation, you can solve this by cross multiplying, right? So you know that 18 times the square root of 3 is going to be equal to 2 times x. That's what's written in this line, right? Square root of 3 times 18 cross multiplied is equal to 2 times x, cross multiplied here. And now just solve for x by dividing both sides by 2, right? So when you divide 18 times the square root of 3 divided by 2, course, you get 9 times the square root of 3. So there's the exact value for x. It's 9 times the square root of 3. So you can write your answer in exact form. But if you, of course, want to have an idea of how big 9 times the square root of 3 is, right, you can use your calculator to get an estimate for square root of 3 and then multiply by 9. It turns out to be, I think, approximately 15.59. This is only approximately, though, right, the length of x. The exact length of x is 9 times the square root of 3. All right, so you'll certainly have problems like number 6, right, on the test, because that's just a very basic application of trigonometry, right, is solving right triangles. Let's move down here to look at another instance where we're solving a right triangle, but in this case, in an application. All right, so here we have kind of an engineering problem. We're trying to or a surveying problem, I should say. We're trying to determine the height here of the Eiffel Tower in Paris, correct? So this famous landmark in Paris, which for I think for many years was the tallest structure in the world, or at least in Europe, probably. And so what we're told in this particular problem is if we move a distance of 2,000 meters away from the base of the Eiffel Tower, then we will get an angle of elevation to the top of the tower of 8.53 degrees. So if you measure this angle of elevation 2,000 meters away from base of the Eiffel Tower, that angle of elevation will end up being 8.53 degrees. And so we want to use this information to determine the height of the Eiffel Tower, right? Okay, well, obviously here, if you think of the Eiffel Tower as being the vertical side of a triangle, right, then in this picture we have a right triangle, correct? And one of the angles in the right triangle, one of the acute angles in the right triangle is 8.53 degrees. So again, we can use our knowledge of trigonometry, right, to solve this right triangle in particular to find the height of the Eiffel Tower. So let's set up a trigonometric ratio, right, involving the 8.53 degrees. Now, of course, this is not a special angle, so you will need your calculator, right, for this problem to finish computing the height. You won't be able to compute the height exactly, correct? All right, so, well, what trigonometric ratio can we use? Well, the h here, right, the height of the Eiffel Tower, this unknown h is the length of this triangle opposite. It's the length of the side opposite the 8.53 degrees, right? And we know the length of the side adjacent to the 8.53 degrees. That's this 2,000 meters, right, along the ground here. So we can set up the tangent, right, of 8.53 degrees, because that is the opposite over the adjacent, correct? That's how tangent is defined. So for this triangle, the opposite is the unknown h, and the adjacent is this length, 2,000 meters. So we know the tangent of 8.53 degrees is h over 2,000, and now we simply solve this equation, pardon me, for h. And again, you can do this by cross multiplying. So just multiply both sides by 2,000, right? And so you'll have 2,000 times the tangent of 8.53 degrees is equal to h. And so in a sense, there's the exact value for the height of the Eiffel Tower. But of course, you'll want to get an estimate for the tangent of 8.53 degrees using your calculator. And so your calculator can do this easily, right? Make sure you're in degree mode and then multiply that by 2,000, and you'll get approximately 300, because that is approximately the height of the Eiffel Tower. It's about 300 meters tall. So there we get our answer there, 300 meters. Now, of course, remember in trigonometry, we also need to be able to compute the trigonometric ratios for angles that are not acute angles. An acute angle means it's between 0 and 90 degrees. So acute is a positive angle between 0 and 90 degrees. But we also need to be able to compute the trig ratios for angles that are bigger than 90 degrees, okay, up to any size. And then also negative angles as well. All right. And so the device we use to compute those trig ratios for these angles bigger than 90 degrees or negative angles is what's called the reference angle. Okay, and so this may be one of the trickier things for you to do on the exam is compute trig ratios using reference angles. And so this is something that I hope you will have practiced extensively before you come to take the test on Wednesday, April 6th, right? So that's the purpose here of problem number 12 on the sample test, is to give you practice computing trig ratios for non-acute angles, angles bigger than 90 degrees or negative angles, using the idea of a reference angle, right? So let's start with probably what's maybe the simplest example here, which is let's find sine and cosine for 135 degrees, which is bigger than 90 degrees, right? So you cannot embed 135 degrees in a right triangle. So so you can't compute the trig ratios for 135 degrees using our right triangle definitions of sine and cosine and tangent, etc. Correct? All right, so what do we do in this case? All right, so here's what is suggested that you do, and here's what I want you to demonstrate for me on the test, right, or in this practice problem. First, let's draw a picture of 135 degrees. So it's pretty easy to draw 135 degrees, right? That is a little bit bigger than 90 degrees, right? In fact, it's 45 degrees past 90 degrees. So it's a positive angle, right? So it's going to open counterclockwise, and it's going to end up over here in the second quadrant, right? Because you're going to open 45 degrees past 90 degrees. 135 is 45 above 90, correct? So here's a picture of this 135 degree angle. Now, to compute its trig ratios, what we have to find is what's called the reference angle for the given angle. And we usually denote that, remember, by using the name of the angle, whatever symbol we're using for the angle, which is frequently theta. And then we put a bar above that. We put a line above that. So I'm calling the reference angle in problem 12 here, I'm always referring to that as theta bar, okay, which is also how we refer to it for class, right? So how do we find the reference angle? Well, what you want to do is starting from the terminal side of the angle, the original angle that you drew, you want to draw the positive angle between that terminal side and the x-axis, okay? So you want to draw the positive angle between the terminal side of your given angle and the x-axis. If you do that properly, you're always going to come out with an acute angle. That means between 0 and 90 degrees. So your reference angle always has to be between 0 and 90 degrees. Remember that, okay? Well, all right, so here's the terminal side of our 135 degree angle, right? Okay, so if we draw the positive angle, that means it's going to go in the counterclockwise direction, right? If you draw the positive angle between the terminal side and the x-axis, you get this angle, which clearly has to be 45 degrees, right? Because remember, 135 is opening 45 degrees into the second quadrant. So this remaining angle between the terminal side and the x-axis has to be 45 degrees, right? These two angles have to add up. The 45 and 135 have to add up to 180, because an open angle, right, angle is 180 degrees. So there it is. Our reference angle is 45 degrees. And now you can compute the sine, cosine, tangent, secant, cosecant, cotangent, etc. For 135 degrees using the reference angle. Just using the reference angle, all you have to do is adjust the signs, okay? Because you want to remember, right, when you're when the terminal side of your angle is in the second quadrant, right, like it is in this case, that's going to change some of the signs of your trigonometric ratios. All right, so what would the sine then of the original angle 135 degrees be? Well, it would be the same as the sine of the reference angle, 45 degrees, except we have to maybe adjust the sign in front of the trig ratio. It could be positive or it could be negative. But in the second quadrant, sine is, and 135 is in the second quadrant, right? In the second quadrant, sine is positive. So we know that a sine of 135 degrees is going to be positive, and it's going to be the same as the sine of 45 degrees. And 45 degrees is a special angle, so I hope you've memorized that the sine of 45 degrees is square root of 2 over 2. So you know the sine of the original angle, 135 degrees, is also positive because it's in the second quadrant, square root of 2 over 2. So when I say it's just that easy, that was a little bit complicated, right? Okay, but still, with the practice, it's not difficult. But you do have to practice. All right. What about the cosine of 135 degrees? Well, it's also going to be the cosine of 45 degrees, possibly with the sign in front adjusted, right? In the second quadrant, however, a cosine is negative because the x-axis is negative in the second quadrant. So you know the cosine of 135 degrees is going to be negative, and then the same as the cosine of 45 degrees, which also is square root of 2 over 2. So again, I hope you've memorized the trig ratios for your special angles, right? All right, let's try another one. So let's try 210 degrees. So if you draw 210 degrees, here's 210. So that's positive. So we go draw in the counterclockwise direction again, right? And that's slightly bigger than 180. So we go slightly past the x-axis here, right? When we're drawing this 210 degree angle, it runs a little bit into the third quadrant. How far into the third quadrant? Well, it's going to go 30 degrees into the third quadrant, right? Because 210 is 30 degrees past 180, right? So we have to move, we have to draw our terminal side 30 degrees into third quadrant. So what that means is quite easily, right, is our reference angle is going to be 30 degrees. Because again, you form the reference angle as the positive acute angle. Acute means less than 90 degrees, right? Between the terminal side of your angle, which is here, and the x-axis. There's the x-axis, right? So that positive angle between the terminal side and the x-axis is going to be 30, is going to be this 30 degrees, right? So your reference angle is 30 degrees. So that means that your sine and cosine of the original angle, 210, are going to be the same as the sine and cosine of the 30, right? Except we have to adjust the SIG in, right, in front of the number. Well, in the third quadrant, both sine and cosine are negative because the x-axis is negative in the third quadrant. So that means the cosine is going to be negative, and the y-axis is negative in the third quadrant. That means the sine is going to be negative as well, right? Remember, sine is associated with the y-axis, cosine is associated with the x-axis. Since both the x and y-axis are negative in the third quadrant, that means both the sine and cosine of 210 degrees are going to be negative. What is the so what is the sine of 210 degrees? Well, it's minus the sine of 30 degrees. But the sine of 30 degrees is 1/2. That's something you should have remembered. So we get minus 1/2 here. What's the cosine of 210 degrees? It's minus the cosine of 30 degrees. The cosine of 30 degrees is square root of 3 over 2. Again, something that you just need to memorize. So there's the exact values of our trig ratios. So on the test, make sure you do not give me, for these angles, since these are special angles, make sure you give me exact values for the trig ratios. Do not give me calculator values, all right? Okay, do not give me estimates. Give me exact values because you can compute those exactly. Let's try another one here. So what about minus 60 degrees? See, here's a negative angle, right? Okay, so if you draw that, here's minus 60 degrees drawn. That's going to be drawn in the clockwise direction. Remember, negative angles are drawn in a clockwise direction, but it only goes 60 degrees, obviously, into the fourth quadrant. So what's the reference angle? The reference angle is always positive, though. it's always drawn in the positive direction, again, between the terminal side and the x-axis. So there's your terminal side. If you draw back up in the positive direction to the x-axis, you get a positive 60-degree angle. So your reference angle is positive 60 degrees. And so that means the sine of minus 60 degrees is going to be the same as the sine of positive 60 degrees, except we have to adjust the sign in front. In the fourth quadrant, sine is negative because the y-axis is negative in the quadrant. So you get minus, the sine of minus 60 degrees is minus the sine of positive 60 degrees. The sine of positive 60 degrees is square root of 3 over 2. So you get minus square root of 3 over 2 here. What about cosine of minus 60 degrees? It's the same as the cosine of 60 degrees, which is 1/2, except we have to adjust the sign again in front. But here, since the x-axis is positive in the first quadrant, remember cosine is associated with the x-axis. Since the x-axis is positive in the first quadrant, I have to just write positive 1/2. What about minus 315 degrees? So let's draw that. That one's a little bit harder to draw. You have to think about where is minus 350 degrees. It's not quite. So it's you're drawing in the clockwise direction because this is a negative angle, but it's not quite one full revolution, right? Because one full revolution in the negative direction would be minus 360 degrees, but you're only going minus 315 degrees. So where you're going to end up here with minus 350 degrees is in the first quadrant, but 45 degrees short of one full negative revolution, right? If you went one full negative revolution, that would be minus 360 degrees. But we only went minus 350 degrees. So we ended up a little bit short of one full negative revolution. How much short? Well, obviously 45 degrees, right? Because minus 315 degrees is 45 degrees away from minus 360 degrees, right? So you end up 45 degrees short of one full negative revolution. That means your reference angle then is going to be positive 45 degrees. Remember, your reference angle is always positive between the x-axis and the terminal side of your angle. So there's our reference angle, and it's positive 45 degrees. So that means that the sine of minus 350 degrees and the cosine of minus 350 degrees are the same as the sine and cosine of 45 degrees, except we have to adjust possibly the sign in front. But here we don't have to adjust the sign in front because our angle ends up in the first quadrant, and in the first quadrant, both sine and cosine are positive. So you can just write a positive result here and a positive result here. What's the sine of 45 degrees? Square root of 2 over 2. So the sine of minus 315 degrees is also square root of 2 over 2. What's the cosine of minus 315 degrees? Same as the cosine of 45 degrees, which is positive square root of 2 over 2. Oh, now let's practice this in radians. Yuck. Okay, so let's do some radians. All right, so where is 4 pi over 3? First, we have to figure out where that is, right, when we draw it. So that's a positive angle. So we're going to draw our angle in the positive direction. Remember, pi over 3 is 60 degrees. So you're going 4 times pi over 3. So you're going to be going pi over 3, which is 60 degrees, 4 times. So you go pi over 3. That's 60 degrees is about right there. Another pi over 3. That would be 2 pi over 3. That puts you in the second quadrant. 3 pi over 3 is the same as pi, which is 180 degrees. So that puts you right here along the x-axis. And then finally, when you go to 4 pi over 3, one more pi over 3, right? You go another pi over 3, another 60 degrees into the third quadrant. So you end up in the third quadrant there, right? About pi over 3 into the third quadrant. Again, remember, pi over 3 is 60 degrees. So we're about 60 degrees into the third quadrant here. So our reference angle is pi over 3, because we're pi over 3 right into the third quadrant, pi over 3 away from x-axis here. So our reference angle is pi over 3. And now you can just compute the sine and cosine by remembering the 4 pi over 3, by remembering the sine and cosine of pi over 3. And then you just have to adjust the signs properly. Remember, you're in the third quadrant. So both the sine and the cosine will be negative. Where's 11 pi over 6? How do we figure out where that is even? Pi over 6, by the way, is 30 degrees. So if you want to sort of mentally think of this as 30 degrees, you're really 11 times pi over 6, which is 30 degrees, which is 330 degrees. So if you want to sort of visualize this angle 11 pi over 6 as being 330 degrees, you can. Notice 330 degrees would be almost one full revolution, but just a little bit short of one full revolution, right? Because one full revolution is 360 degrees, and this is 330 degrees. Another way of thinking of this is 11 pi over 6, that's almost 12 pi over 6. 12 pi over 6 reduces to 2 pi. So we're almost at we're almost at an angle of 2 pi, right? 11 pi over 6 is almost 12 pi over 6, which is 2 pi. But 2 pi is one full revolution. So we're just a little bit short of one full revolution. How much short? Well, again, one full revolution is 12 pi over 6. We're at 11 pi over 6. That means we're pi over 6, 1 pi over 6 short of one full revolution. There's a picture of it, right? So there's our 11 pi over 6, almost one full revolution, except we're pi over 6 short of one full revolution. That means our reference angle is pi over 6, right? Because the positive angle between the terminal side and the x-axis will be this angle, pi over 6. And now you can just use your reference angle, right, to compute the sine and cosine of the original 11 pi over 6. They'll be the same as the sine and cosine of pi over 6, except again, we have to adjust the signs. See if we can draw two more reference angles. These are not too bad. So what about 7 pi over 4? I'm going to think of this like I did the previous example. 7 pi over 4 is almost 8 pi over 4. 8 pi over 4 reduces to 2 pi. So we're almost one full revolution, because one full revolution would be 2 pi or 8 pi over 4. But we're only at 7 pi over 4. So that means we missed one full revolution by pi over 4. So again, our reference angle is pi over 4. And right, there's a picture of it. There's 7 pi over 4. Pi over 4 short of one full revolution. That would be 8 pi over 4 instead of 7 pi over 4. So we're pi over 4 short of one full revolution. So our reference angle here is pi over 4. And now you can use this angle, right, to compute the sine and cosine of original 7 pi over 4. Sine and cosine of 7 pi over 4 will be the same as the sine and cosine of pi over 4, which, by the way, is the square root of 2 over 2 in both cases, because pi over 4 is the same as 45 degrees, except we have to adjust the signs. In this case, sine will be negative because we're in the fourth quadrant. Sine is negative because the y-axis is negative in the fourth quadrant, but the cosine will stay positive because in the fourth quadrant, cosine is positive because the x-axis is positive in the. Finally, let's see, where is minus 2 pi over 3? So that angle we're going to draw in the negative direction, right? That means in the clockwise direction. So let's think of that as going pi over 3 twice, right? But in the negative direction. So we go pi over 3 once. That's about 60 degrees. Well, that's exactly 60 degrees, pi over 3. And then we go pi over 3 a second time, another 60 degrees. Whoops, another 60 degrees here. And that moves us into the third quadrant. What's the reference angle then? Remember, you have to draw that between the x-axis and the terminal side of the angle. So here's the reference angle, and that's going to be pi over 3, because this 2 pi over 3 and this pi over 3 have to add up to be a full pi, right? Because an open angle is pi, or 180 degrees. So our reference angle here is pi over 3. And again, use that to compute the sine and cosine of the original angle minus 2 pi over 3. Just adjust the signs based on the quadrant that the terminal side is in. Okay, well, I hope that quick review there helped you a little bit with calling how to compute reference angles. Again, it's important you practice that right before the test, especially since we haven't done this for a while, right? So you're going to need some practice with that prior to taking that test on Wednesday. Okay, let's switch to a topic that you're likely to find easier than trigonometry, which is also very important in calculus, and that's identifying where functions are increasing and where they're decreasing, and then also locating the turning points for functions, right? So a turning point is where a function switches from increasing to decreasing or vice versa. And then also local extrema. So that would be local maximum values and local minimum values, if there are any. Okay, so let's start with a pretty straightforward example of this function that we're given a graph of. In calculus now, you're going to be concerned with discovering this information or these sorts of answers without using a graph, okay? So just from the formula function, and that will allow you to give exact answers to these questions. But since we haven't got to calculus yet, right, or you haven't got to calculus yet, we're going to rely on a graph to answer these questions. So here we have a graph of function. This looks like it's just a parabola. And so let's see where it's increasing. So remember, just sort of scan the function from left to right, right? The graph of the function from left to right. And where the curve is going down, that's where the curve is decreasing. Where the curve is going up, that's where the curve is increasing. It's just that simple. But remember, you want to give your answers in terms of the x-axis. So not in terms of y values, but in terms of x values. So that's why we're scanning the curve or the graph from left to right here. So as you move from left to right here along the x-axis in this graph, notice at first the curve is falling, right? And apparently, since the curve is not cut off here, I guess we're left to assume that this curve extends in the same fashion, right? All the way to the left along the x-axis. So that means this curve is going to be decreasing starting at minus infinity on the x-axis and then going up to this point, right, where it switches from decreasing to increasing, and that's at 4 on the x-axis. So this curve is decreasing from minus infinity to 4, right? Remember, we're going to write our answer in interval notation. So starting at minus infinity and going up to 4, and you can use a square bracket. You can include the boundary value here 4 in the set where the curve is or the function is decreasing. Then of course it begins increasing where it stops decreasing, right? So that's also at 4, and it looks like it's going to continue increasing indefinitely here along the x-axis to the right. So apparently that behavior extends to positive infinity. So here's where the curve is increasing. So we have a switch, right, from decreasing to increasing right here at 4 on the x-axis. So that means this is a turning point. So the coordinates of our turning point are 4, right, is the x coordinate, and it looks like 2 is the y coordinate. Of course, we're only giving estimates here now, right, because we're reading from the graph. Again, in calculus, we'll be able, using the formula for curve, to get exact answers to these questions. You won't have to rely on just visual estimates. What are our local maximum values? Well, we don't have a local maximum right here. We don't have a peak turning point, but we do have this valley turning point. And so, and of course, its coordinates are 4 and 2, right? And so that means our local minimum value here is 2. That's the y coordinate of the turning point. But you could write also the turning point coordinates for 2 as the answer to this question. we sometimes answer this question in the form of a point instead of just a single value. 2 is technically the exact correct answer, but if you put 4,2 here as well, that would be all right. All right, let's try another one. Now, this is kind of a trick question that I threw in. This is just a straight line with positive slope. So notice this function is always increasing from left to right, right? It's always going up. It doesn't change behaviors, right, from increasing to decreasing. So that means the intervals where this is increasing is just the whole domain of the function, which is the entire x-axis, which is minus infinity to infinity. And so you don't have any intervals where this curve is decreasing. And since it never switches from increasing to decreasing or vice versa, that means you don't have any turning points. And if you don't have any turning points, you cannot have any local maximum values or local minimum values. Now, C also is not quite a straight line, but it's also kind of a trick question. This is a piecewise linear function because it has, the graph is composed of 2 pieces, but both of which are straight lines, right? And both lines have positive slope. So this function also is always increasing, right? It's increasing from the left all the way to the right. It never starts decreasing. It never starts going down. So you don't have a change in behavior. This curve is always increasing from minus infinity to infinity. It's not always increasing at the same rate, however. Okay, so this part of the curve is all obviously right, increasing faster than this part of the curve because this line has bigger positive slope than this line does. So it's not always increasing at the same rate, but it's always increasing. So that means that you don't have any intervals where it's decreasing, and therefore you don't have any turning points because it never changes behavior from increasing to decreasing or vice versa. You don't have any turning points. You don't have any local maximum minimum values. Now, this point is not a turning point. All right. So obviously you have a bend in the curve here, but that is not a turning point. Okay. Because to get a true turning point, the curve has to switch from increasing to decreasing or vice versa. Here, it is continuing to increase past this point, just not at the same rate. See if we can find one that's a little bit more interesting. This also is piecewise linear, right? Okay, because this function consists of 2 pieces, or this graph consists of 2 pieces, both of which are straight lines. But here you do have a change in behavior, right? A change in direction. That's the behavior I'm just mentioning here, the direction of the function at this point, right? Because here on the left, right, function is decreasing. This straight line has negative slope. And then here on the right, here the curve is increasing, right? Because this line has positive slope. So you have a switch from decreasing to increasing at this point. So it's increasing from -2 to apparently infinity, right? The right-hand part of the curve is increasing, of the function is increasing. The left-hand part of the function is decreasing. So it's decreasing from minus infinity to -2. -2 here give your answers to where a curve is increasing or decreasing, where a function is increasing or decreasing in terms of the x-axis. So we do have a turning point here because we have a switch from decreasing to increasing. So this is a proper turning point in this example. Coordinates are -2 and 0. This is a valley turning point. So you have a local minimum here, and the local minimum is the y-coordinate of this turning point. So that is 0. No maximum values because you don't have any peak turning points here. Finally, let's look at one more. This is more typical of an example you would see in calculus. So here you have a nice smooth curve. It's not a piecewise linear curve, right? It's a nice smooth twisty curve here, right? And so let's talk about its direction, where it's increasing and where it's decreasing. So if we span the curve from left to right, we see at first it's increasing, correct, right? This portion of the function is increasing, and that continues until we hit 0 on the x-axis. Now, don't say it continues up to 4, okay? It continues to 0 on the x-axis. And then it's decreasing for a while, and then it begins increasing again here at 6 on the x-axis. So where is this function increasing? From minus infinity to 0, this part minus infinity to 0 on the x-axis, and this part starting at 6 and to infinity. So you get two separate places where this curve is increasing. You combine those two separate sets, right, with this union operation. Where is the curve decreasing? In the middle here, right, starting at 0 on the x-axis and going up to 6 on the x-axis. So it's decreasing from 0 to 6. Don't say it's decreasing from 4 to minus 4. I know that's what you're going to want to put here, right? It's decreasing 4 to minus 4, but give your answer in terms of the x-axis. So it's decreasing from 0 to 6. This one has two turning points because two places where it switches direction. Right here, it switches from increasing to decreasing. So this is a turning point. So you have a turning point at 0, 4, and then you have another turning point here where it switches from decreasing to increasing at 6 and minus. What's our local maximum value? This peak turning point gives us a local maximum. What's the y-coordinate of this turning point? It's 4. So the local maximum value is 4, and the local minimum is the y-coordinate of this valley turning point, which is minus. I think you'll do well on this portion of the test, where you're just writing down answers to function direction. One way we measure how fast a curve or a function is increasing or decreasing is by using a calculation called the average rate of change. And remember, the average rate of change is really just the same calculation as slope of a line. It's just we apply that concept to curves instead of straight lines. So let's look at this problem 16. Here we're given not the formula for a function, but the graph of a function. This is called the surge function, which is useful in medicine. And what this function depicts is the amount of aspirin in milligrams circulating in the blood of someone X hours after they have consumed 350 milligrams of aspirin, which I think is kind of the standard dose for aspirin. And of course, you see what happens here is what you would expect, right? At first, you're going to get a surge, right, of aspirin in the bloodstream, right, as that aspirin is absorbed. And then, of course, your liver and kidneys begin metabolizing that aspirin out of your bloodstream, correct, right? Because your body thinks that aspirin is really not supposed to be there, right? So it's going to take it out of your bloodstream slowly, right? So you have a certain amount of time, right, that you've got aspirin circulating in your bloodstream, and so you're going to feel the effects of that, right? The anti-inflammatory effects of that aspirin. But then, of course, those eventually wear off, so you have to repeat the dose there eventually, correct? All right, so now the curve here is the curve of the function. This line that I've drawn is something that I've superimposed on the graph, and that's because that's an answer to one of the questions here. So that's the very first question in this problem number 16 on the sample test. It says plot the secant line, x equals 1 to x equal 3. So a secant line for a curve is a straight line. I'm sorry, the secant line for a curve is a straight line that connects 2 points on the curve. So we're trying to draw the secant line connecting the point on the curve that corresponds to x equals 1. So that's this point on the curve, right? And to the point x equals 3 on the curve, right? Which is this point. So we just plot those 2 points on the curve where x is 1 and where x is 3, and then we just connect them with the straight line. That's called the secant line. And the reason we draw secant lines is so that we can sort of treat curves like straight lines, even though curves are not straight lines, right? Okay. And One reason why we want to be able to treat curves like straight lines is we can compute slopes of straight lines, and slopes of straight lines then slopes of secant lines, I should say, give us a mechanism for sort of talking about a curve as though it were a straight line, or applying concepts that apply to straight lines to curves, like the concept of slope. And that's exactly what average rate of change is. It's just the slope of a secant line. It's just treating a curve as though it were a straight line. So in part B here, it says estimate the slope of the secant line drawn in problem 1. So all I did here is try to estimate the coordinates of these 2 points. Of course, I know the x coordinates are 1 and 3. I also estimated the y coordinates of these 2 points. And then I just calculated the slope using those two points, right? The coordinates for those 2 points. So I think I estimated the coordinates of the points on the curve, the endpoints of the secant line, as being 1 and 275, and then 3 and 50. And then I just calculated the slope between those 2 points using the familiar slope, right? And so we get minus 112.5. So that's the slope of the secant line, but that is what we call the average rate of change of the curve, okay? And again, the purpose of average rate of change is to give us an idea, a way of measuring how fast a curve is increasing or decreasing. So the average rate of change of this curve from x equal 1 to x equal 3 is the slope of the secant line that connects x equal 1 and x equal 3 on the curve. So this answer is really just the same as this one. I don't have to do any work here. The average rate of change is the same as the slope of the secant line. That's minus 112.5, right? Now, again, what's the value of that number, minus 112.5, the slope of that secant line? Because it gives us a chance to, or a way of describing how fast a curve is increasing, decreasing. So that's part D here. So suppose that separately, we estimated the average rate of change of this curve from x equal 2 to x equal 4 was minus 62.5. So I didn't draw that secant line from x equal 2 to x equal 4. There's x equal 2 is up here, right? So there's x equal 2 is a point about here, right? X equal 4 is a point about right there. So imagine that I drew the secant line between those 2 points and estimated its slope, and I came out with minus 62.5, right? So imagine that we had done that. And what we want to know is what's the meaning of that average rate of change, minus 62.5. So we want to interpret its meaning. And so what that tells us is that on average, from x equal 2 to x equal 4, so in other words, from hour 2 to hour 4, because x is measuring elapsed time in hours, the amount of aspirin circulating in the blood was decreasing because this number is negative, right, by 62.5 milligrams per hour, right? So average rate of change gives us a way of describing how fast a curve is increasing or decreasing, like slope gives us a way of describing how fast a line is increasing or decreasing, right? Probably you will have an interpretation like this one on the test of average rate of change. So make sure you have reviewed that on the sample test in your notes, right? So you will be able to write down that interpretation correctly. All right, let's look at one last problem then. This one involves some algebra. So this one might be a little bit more time consuming than other problems on the test. And this is another average rate of change calculation, but no interpretation here because this is a very abstract problem. Here we're given a function, formula for a function, not the graph of a function. So 2x squared plus x is the formula function, and we want to find the average rate of change from x equal to, but we're not given a specific number here. We're just given an unknown starting point a up to a terminal value a little bit to the right of A, right? A plus H. So some number A and then a number a little bit bigger than A, namely A plus H. So let's see if we can calculate the average rate of change of this function from A, x equal A, to x equal A plus H. All right, so we're going to have to do some symbolic arithmetic here. Symbolic arithmetic, better known to you as algebra. We're going to have to do some algebra here, right, in calculating this average rate of change. But remember, average rate of change is just the slope calculation, right? So you're going to take f of A plus H, that's your second y value, f of A plus H minus f of A, and then divide that by the difference in the two x values, which would be A plus H minus A. So that's the average rate of change formula. So f of A plus H, that just means you plug A plus H in for x, right, in your function. So you get 2 times A plus H squared. Instead of x squared, you get 2 times A plus H squared plus A plus H. And then minus f of A is going to be, well, just plug A in for x in this formula. So you get 2a squared plus A. So you subtract off the f of A. Make sure you put this, subtract off the entire quantity f of A. So put it in parentheses. F of A is 2a squared plus A, right? Make sure you put that in parentheses so you make it clear you're subtracting the entire quantity, right? F of A, otherwise you're going to make a sign mistake here. So we have a little bit of algebra to do to simplify the numerator in this average rate of change calculation. Of course, the bottom is easy to simplify. You just have A plus H minus A, so the A's cancel and you just get H. Ultimately, all of this is going to simplify quite nicely to our final answer, which is down here on right. All right, so let's see if we can simplify 2 times A plus H squared plus A plus H, right? Well, remember, when you square A plus H, that means A plus H times itself, A plus H times A plus H. And then, of course, we have this plus A and H, right? And then minus the quantity in parentheses. So I'm going to remove the parentheses by distributing the minus sign. So I get minus 2a squared minus A. All right, before we start canceling things, because some things are going to start canceling here in this numerator, let's go ahead and multiply the A plus H times the A plus H. So be sure you multiply these parentheses properly, right? Get A times A, that's A squared. You get A times H, and then you get H times A, which is the same as A times H. So you're going to get A times H twice. So that's why we get this middle term, 2 times A plus H, and then H times H is H squared. Don't forget you're multiplying all of this by 2. So I'm going to put this product inside of parentheses, because all of that has to ultimately be multiplied by the 2. And then, of course, we still have the plus A plus H minus 2a squared minus 2a. Now let's distribute, let's say minus A. Let's distribute the 2 now. So when you multiply the 2 through, you get 2a squared, right, plus 4ah, 2 times 2 is 4, right? So plus 4ah plus 2h squared, and then, of course, the rest of it. Now we can cancel some similar terms, right? You have 2a squared minus 2a squared, so that goes away. What else do we have? We have plus a and minus a, right? So that goes away. And so we get left with 4ah, this is left, plus 2h squared, and then plus this h. Everything else has canceled. Now, fortunately, and this often happens when you're simplifying these average rate of change calculations, you have h in all 3 terms in your numerator, and you're dividing by h. So that means you can divide all of these h's out. So you end up with this h dividing out. You just get left with a. One of these h's will divide out. This is h squared, so only one of them will divide out. So you get left with 2h. And then finally, last here, h over h, this h divides out and leaves you with 1. Not with 0, but with 1, right? H divided by h is 1. So there's our last answer then, our final simplified result. It's just 4a plus 2h plus 1. Okay, so other problems here from the practice test. This is all I'm going to review on this tape. But other problems from the practice test we will look at in class on Monday, April